Once again, welcome to MSB lecture series on main group chemistry. In my previous lecture, I was discussing about molecular orbital theory and its utility in explaining bonding in simple diatomic molecules such as H2 to second row p block elements. I told you about how one can use MO diagrams to explain bond strength and bond distance and all those things by just looking into the number of electrons present in bonding orbitals and number of electrons present in anti-bonding orbitals. So, that will give you some magnitude of bond order. Based on bond order, bond strength and bond enthalpy can be assessed. So, now before I proceed further for heterodiatomic molecules or polyatomic molecules, let me write MO diagram for F2 molecule. Always remember to write arrow to show energy, and here 2p and another 2p from another fluorine atom. Then we have 2s, and then we have 1s. We have 1s. So, here we will make bonding and anti-bonding sigma and sigma star. We have 2 electron here, 2 electron here. So, this shows the core electrons do not contribute to the bonding. So, because here the bond order is 0, that is the reason most of the cases we ignore the writing MO diagrams for core electrons. Now, it is for so again sigma and sigma star, again we have 2 electron each. So, now what we have is sigma pi another sigma. So, that is sigma star, here it is pi star, and here it is pi, and it is sigma. So, now we have here 5 electrons are there, 1, 2 like this, and now another 4 electrons will come here. So, now let us look into the bond order. This is F atomic orbital, and here atomic orbital of F and MO for F2. Let us look into the bond order. Because here these are cancelled, no point in counting here. So, we shall count here 2, 4, 6 minus 4 in anti-bonding. So, divided by 2 will give you 2 by 2, 1. So, between F and F there is a single bond. So, we should be able to write MO diagram and also depict the bond order here. So, we have a single bond between 2 fluorine atoms in F2. So, when we write for a heterodiatomic molecule that results in the formation of a polar covalent compound. In these kind of polar covalent compounds, bonding molecular orbitals are closer in energy to the atomic orbitals of the more electronegative atom, and also the anti-bonding molecular orbitals will be closer to the energy of atomic orbitals of least electronegative atom. For example, I am taking 2 atoms of the same element. Then if you take this one, whether you consider bonding or anti-bonding molecular orbital, they are at equidistant from both the energy of both atomic orbitals in their free state or isolated state. But if I take something like this, one with low electronegativity higher in energy and other one with more electronegativity lower in energy. So, when they are combined, obviously when we generate molecular orbitals, the bonding molecular orbital will be closer to the one which is more electronegative, and obviously another antibonding molecular orbital will be closer to the atomic orbitals of least electronegative atom, something like this. For example, if I consider one here, okay, less electronegative, another one is more electronegative, atomic orbital, and here atomic orbital, and if I constitute molecular orbital something like this. So, this is the bonding molecular orbital and this is anti-bonding molecular orbital. So, here you can see this one will be much closer to the energy of isolated atomic orbitals having least electronegativity. So, this one should remember always when we write a diatomic molecule or for a covalent compound, we should consider the electronegativity and accordingly we should write their energy. So, that is the reason I am telling you we should be extremely careful in always mentioning this arrow and that mentions about that indicates the energy of the orbitals. Now, let me consider one such molecule, that is NO. We have N and O. N is little less electronegative compared to oxygen. Let me write the MO diagram. So, here I am considering 2p atomic orbital of nitrogen and little lower in energy, 2p atomic orbital of oxygen, and then I am considering here 2s. So, this will give this sigma and sigma star of 2s is completed. So, now first what we have is here pi 2p and then we have sigma 2p and then we have pi star 2p and sigma star 2p. So, now we have here 3 electrons 2s to 2p 3, here we have 2s to 2p 4. So, like this. Now, we have to arrange these 7 electrons. So, these two are filled, these two are filled. Okay. So, we have one electron that comes here, it comes to the pi star, okay, anti-bonding orbital. So, let us look into this is MO for NO. Let us look into the bond order. Bond order equals we have 6 electrons here and 1 electron here. So, this is 2.5. Okay. So, bond order of NO is 2.5. that is the reason NO has a tendency to lose the lone electron present in anti-bonding orbital to get extra stability. Once if you remove that one, it becomes NO plus. When it is NO plus, we do not have any electron in. This is for NO. Similarly, if you remove this electron, so it will be NO plus will be 6 by 2, it will be 3. So, NO bond is getting stabilized. That is the reason this NO ligand has a tendency to act as a cationic ligand by eliminating the electron present in the anti-bonding orbital. That means about the character, about the reactivity and properties of molecules can be predicted simply by writing MO diagram and looking into the electronic arrangement in the bonding and anti-bonding orbitals. Okay. So, this diagram what I have shown shows the relative energy of various atomic orbitals, and when they form diatomic molecules, especially I have given here for second row elements, how that is changing gradually you can see as we move from left to the right of the periodic table, electronegativity is steadily increasing. As a result, what happens are electrons are coming more and more close to the nucleus because of the increased effective nuclear charge. As a result, what happens, the shells in which the electrons are present are also orbitals are also pulled more closer towards the nucleus. In this context, what happens, the energy steadily drops. You can see here from starting from lithium to neon, energy steadily dropping. At N2 it crashes here. Okay. You can see here this sigma will be lower in energy compared to 2, that is Pz will be lower in energy and then this will be in higher in energy. This is what exactly happens. That is the reason I wrote 2 different diagrams for molecules up to nitrogen and nitrogen onwards, oxygen, fluorine and neon. The trend changes, the sigma p will be sigma 2p will be lower in energy compared to pi 2p. So, this one should remember, and also this diagram is there in most of the textbooks, you can just have a look at it. Okay. So, in this one just I have shown here as the electronegativity increases, as the orbitals come more and more towards the nucleus, there is a possibility of mixing of atomic orbitals even before the molecules being formed. So, here without mixing MO pattern occurs as expected here. I have shown MO diagram with mixing, without mixing. The first one is here without mixing. You can see here without mixing is similar to what I wrote for several molecules in my last lectures. And also here due to the mixing, basically what happens, the sp mixing occurs, the orbital shift is shown here. So, sigma orbital will be higher in energy than the pi p orbitals. As a result, you can come across some sort of mixing and more refined molecular orbitals in fact show mixing of s as well as pz while the formation of sigma orbital, and also similarly px py do not mix with s orbital. So, I will show you some more MO diagrams where we can visualize how this mixing occurs prior to the formation of molecular orbitals. With this, so let me write MO diagram for water molecule. So, in water we have 2 hydrogens having 1s electron each will be combining with oxygen to form 2 OH bonds. From VS-CPR theory as well as valence bond theory, we know the fact that oxygen in water is tetrahedral with 2 lone pairs and 2 bonded pairs, and the shape of water molecule is bent or V shape. Okay. So, here I am considering 2p orbitals of oxygen, and then here I am considering 2s orbital. Here ligand group orbital we are considering, and here one and another one here, and of course here we call this H2 bonding and H2 anti bonding. Okay. So, this is with A1 symmetry, this is with B2 symmetry, and these are all called Mulliken symbols. At present you may not be familiar with what is A1, what is B2, how these Mulliken symbols are given. For that one should have the knowledge of group theory. Perhaps when you study group theory and when you go for understanding the spectroscopy features of coordination compounds, I am sure you will understand Mulliken symbols. Right now I am not going to dig deep into the Mulliken symbols, simply you should remember here we have Mulliken symbols for this one. This is for bonding H2, we have A1, and anti bonding we have B2. Okay. And now we are considering, of course here we have 2px, 2py and 2pz. So, for this also 2px is called has B1 symmetry and 2py has B2 symmetry and 2pz has A1 symmetry, and of course here S always has A1 symmetry. And now we are considering here we have total of 2 electrons are coming from 2 hydrogen atoms, and now we have here 6 electrons are coming from oxygen. Okay, so, let me write them here. Okay. So, this is A1 and this is B2 and this is A1. So, this is not there, ignore this one, this is B1 and this is B2 and this is A1. These two are anti-bonding. So, here now I start filling. So, total we have to this is not there. So, what we have is 6 electrons here plus 2, 8 electrons are there. We start fill those things, 2 electrons are here and 2 are here and 2 more are here and 2 more are here. So, now let me start connecting this one. So, we have to connect now the similar ones A1, A1 and so here A1 and of course, here also A1 is there, it should be connected. Okay. Now, B1 is there. So, B2 is from here you should connect to this one and B2 is also here, it should be connected. And now, B1 we do not have any, so it remains as non-bonding. Okay, B1 the corresponding we do not have, it remains as non-bonding. So, now B2 is connected here and A1 is connected here and then A1 is connected here and B2 is connected here. Okay. So, now let us look into this diagram here. Okay. This represents these 2 electrons here and these 2 electrons represent the presence of 2 OH bonds, and then these 2 electrons and these 2 electrons represent the 2 lone pairs present on oxygen atom in water molecule. For example, if I write something like this, okay, I can simply correlate this one to this one of this bond and this one to one of the other bond, and then here we have 2 lone pairs. Okay. So, one of this one will be represent this lone pair and another one represent this lone pair. So, this is how you can clearly write the MO diagram for even a triatomic molecule like water. Of course, one can also write for polyatomic molecules that I will be considering in a few minutes time. Hope you have understood how to write the MO diagram for water molecule. I already discussed it. NO plus has a stronger NO bond because bond order is 3, whereas in simple NO, where due to the presence of one electron in the antibonding orbital, it has a bond order of 2.5. Now, let us consider another important molecule such as CO. MO for CO molecule, MO diagram for CO molecule. So, here we have carbon and oxygen. Oxygen being a more electronegative, its energy both 2s and 2p energy will be relatively lower compared to the energy of 2s and 2p. So, we have to keep that in mind always. So, here let me write 2s for C, atomic orbitals of carbon, and then I write here for 2p, and then at relatively lower level I write for oxygen and also 2s for oxygen, atomic orbitals of oxygen here, and here we have 4 electrons. In this case we have 6 electrons. So, first there will be, I am showing you the mixing now, both 2s and 2p they mix, and just remember which orbital 2s is mixing and what is the nature of that bonding, whether it is sigma bonding or pi bonding. So, here let me write relative energies, one here, one here, so here it is sigma called 1 sigma, here 2 sigma and pi 2p and 3 sigma pi star 2p and 3 sigma star. So, this is another way of representing. So, now these two has to be connected here, and then this also get connected this one, and this also shows connection with both. Okay, and then this also shows connection with this one. Whereas this one there is no connection from 2p because 2s will not participate in pi bonding. Okay, but 2s can correspond to this one. Something like this. Let me start writing the electrons here. Okay, and then here 2, 4, and then here we have total 6 electrons. Now the bond order, this is for MO for CO. I will show you again. So, 2p we have 2 electrons and 2p we have 4 electrons, it is little lower in energy, and then we have 2s orbital and 2s orbital here, both have 2 electrons. Now, 2s has symmetry for sigma, all sigmas interact with 2s, it is head on end to end overlapping. So, here all are connected, whereas pi does not connect with 2s. So, it shows only interaction of these 2p orbitals of carbon as well as oxygen to form. Now, we have total of 4 plus 6, 8 electrons are there, they are filled here, okay, 2, 4, 6, 8. Okay. So, 8 electrons are there. Now, let us look into the bond order. 6 minus 0 by 2, this is 3. So, this represents very clearly 3 bonds between carbon and oxygen, out of which one is sigma and 2 are pi, that can also be seen here. Same information we got from valence bond theory. And also when we look into Lewis dot structure, this is how we wrote initially. So, here the total number of 10 electrons. So, here these two are coming here and these two are coming here in order to give octet for both. So, as a result we had this kind of situation. So, here these two lone pairs on carbon makes carbon monoxide a soft Lewis base, and here you can see triple bond is there, same information we are also getting from carbon monoxide MO diagram. Okay. So, in my next lecture, so I would discuss about more interesting molecules such as carbon dioxide and BH3, BF3, and also hexa coordinated sulfur compound, sulfur hexafluoride, very interesting. And also we can make an analogy of the geometry and the structure information we get for SF6 from MO diagram to what we have predicted its octahedral geometry from valence bond theory using hybridization concept. Let us consider those two things, and whether any difference is there or whether any anomaly is there, we shall look into those things in my next lecture. Until then, have a pleasant chemistry reading. Thank you.